This conference will now be recorded.
So just let me know when you need the slides advanced.
Okay, great. Thank you. So should we start? I think it's about 2 o'clock. All right. Can you see me? Okay, great. Hi, everybody. Let me introduce myself first. My name is Yan. I work at OSTI Modeling Program Office. So I'm going to speak first, then the OER WPO representative is going to introduce the program next. This is jointly sponsored by the two offices. So the goal is to inform from research to modeling, then to operation. Can you go to next slide? Karen, do you want to go through this logistics slides?
Sure, just really quickly, Bonnie already touched on making sure that you are muted if you're not speaking, and also to turn off your webcam to preserve the bandwidth, and then the presenters will share their screen. And for question and answers, we're going to use a discussion document. I put the link to that in the chat, so if everyone could click on that, and if you don't have access, please request access, and I have it up and I will grant access right away. So please use this document for chatting back and forth or any questions, and then you can continue to ask questions to the speakers after the talk today.
Next slides, please. Yeah, so today's we are going to have two speakers. Jessie and I prepared a few slides to introduce this webinar. Next slide. Let me first introduce the staff from our office. I'm going to invite the division director, the modeling program division, Dr. Darcy Koch, to speak a few words about this program. Darcy, can you put on your, okay, great.
Yeah, hi. So thanks, Yan, and welcome to everybody. I'm very excited about this new activity that Yan and Jessie and folks in our teams have put together. I think, as Yan said, this is really important for our forecast systems because we're moving more and more towards coupled modeling and longer time scales. And developing coupled DA and all of the challenges that go along with that. And it's really, really critical that we have the research community helping the model developers and the forecast developers understand what's needed to improve predictability for different phenomena, and at the same time to have the forecast community and CPC giving feedback to the research developers. So I'm very excited that they put this together. So welcome everyone to the first one. So yeah, I'm Dorothy Koch, the Division Director of Modeling Program, and you've met Yan, and Karen is providing support. We also have Deepthi, who is one of the contractors who's also very involved in a medium to extended range, particularly interested in the metrics which need to be defined for these longer time scales. And then finally, Farida is a contract staff member who is the project engineer on the UFS R2O project. That's the main effort that we have right now in developing the extended range forecast system. So welcome again. Thanks, everyone.
Thank you, Darcy. Next slide, please. Yeah, this slide just give you a introduction about this office, what we do in this extended range time scale. Like Darcy mentioned, she has been leading this effort, working with WPO EPIC program to set up this so-called UFS R2O project that includes the researchers from EMC, from normal labs, from universities. So it's going to be build the system using the unified framework, means unified coupling, unified DA, unified post-processing and pre-processing and evaluation. So this program, we are going to support this extended range application, so-called mini range combined with S2S, meaning the couple system is used from day one integration all the way to week 3, 4, then to the seasonal to 1 year. This system is a big effort. It's going to be a target to be implemented in 2024 and 25. So we really need the community helps to build this system. So on the first image on the top left is this team, the S2S application team with this modeling, DA, physics, and atmospheric aerosol composition. So we want to work with the S2S science, that effort by WPO, explore all the science priorities, like from stratosphere, RC coupling, land. So we want to connect this with the NWS effort. We have this NOFO, notice funding opportunity to try to focus on the R2O aspect of the program. At the same time, we are supporting the forecast products development at CPC to deliver the societal benefits impacts. And also we have been working with the multi-agency efforts as well with OER, WPO, CPO, NASA, and NCAR. So finally, we work with WPO, try to enhance this R2O communication, because this includes both the forecasters, the model developers from UFS, and also the research community on the S2S science. So this webinar is mainly to enhance the communication across all the different groups. Then I'm going to, next slide, I'm going to give the floor to Mark Olsen, who is going to speak for the WPO program.
Hi, everyone. Thank you, Jan. As she said, I'm Mark Olsen. I am the Deputy Program Manager of the S2S program in the Weather Prediction Office. The Program Manager, Jesse Carmen, is unable to be here, at least for the first half of today. She may be able to join later. But let me introduce the rest of the staff here. Maureen Brooks and Bonnie Brown serve as program coordinators with us, helping out immensely. And go ahead to the next slide. And I did want to say a couple words about the webinar series itself. As you know, a lot of this information was actually in the emails that you might have received, but this will be a monthly webinar. You know, we've nominally chosen the first Monday of each month at 2 o'clock, and our goal here is to provide a relaxed, informal forum where weeks 3, 4, and S2S research can be shared and discussed. Now, even though we're really kind of supporting the research funded by the 2 line offices, this is not a reporting requirement. And our goal here is to really create a forum for dialogue among the forecasters, modelers, and researchers. Now, each month we'll generally have 2 15 to 25-minute talks, and hopefully ample time for questions and discussions, which might be kind of a little bit shorter today on the questions and discussion due to us giving some of this background info up front here. But we also don't ask that all the talks be polished science talks of a complete project. In fact, we hope that not every talk is a polished science talk. We want to be able to include intermediate results, that can benefit from discussion with the community and so forth. And this also includes like practice talks for conferences, graduate student talks. Somebody has a new idea, they just want to talk about it a little bit. Anything that can really benefit from sharing or getting feedback from the community. Go ahead to the next slide. So many of you are already on the email list. If you are not getting emails about this and you want to be added to the email list, please go ahead and contact Karen Keith. Her email address is given right there. And we also have a website with a schedule and other things, and that exists at the link that is shown on the screen right now. Right now, it is really only shared within NOAA and people with a Google account. Right now, if you have a Google account and you try to access it, I think you can ask for permission and we'll be able to give it to you, but we're working on trying to get it accessible outside of NOAA without a Google account. So the website also has a form for requesting a time to speak. Speaking slots right now are available beginning in December, and hopefully they'll fill up fast. And in fact, if you cannot access the website, but you would like a time to speak, I would suggest contacting Karen Keith as well at the email address listed up at the top there. And finally, before turning it over to the first talk, I do want to say, go ahead, feel free to pass along this webinar series info, wide and near and wide to any potentially interested people. I think grad students and postdocs could benefit from this and also provide good discussion themselves. So feel free to advertise this as you see fit to any potentially interested people. So with that, I will turn it over to our first speaker. I think that will be Dr. Wang. And we'll go ahead and switch the slides and make her a presenter and let her take away the first talk. So thank you very much.
Can you see my slide?
Yes, we can see
Yes,
it.
we can.
Okay, great. Thank you. Let me switch to slideshow mode.
Dr. Wang, if you want to, you can turn on your webcam.
Oh, okay. Let's see where to. Okay. Okay, thank you very much. As mentioned in the introduction part, I think this webinar series will be a great forum to promote S2S prediction. I really appreciate the opportunity to present at the webinar series. The title of my talk is Hybrid Prediction of Weekly Tornado Activity Utilizing Weather Regimes. This study is part of my student Doug Miller's thesis research. It is done with my colleague Jeff Trapp at UIUC and Dr. Dan Hanos from CPC. It is supported by the NOAA MAP program. Okay. Let's first take a quick look at the current predictability limit for severe storms. The plots we see here are from the Storm Prediction Center related to the tornado outbreak in May 2015. We can see the outlook from day 1 to day 6. From day 1 to day 6, the forecasts are pretty skillful in capturing the outbreak in central United States. But beyond 3 days, you can see the potential is too low. This is what is shown in the forecast website. That means the probability of tornado activity or severe storms is less than 15%. This is commonly seen beyond 3 days. Overall, tornado outlooks are less skillful than hail or wind forecasts. And it's not a surprise. When we move on to the sub-seasonal timescale, tornado prediction is also a big challenge. Generally speaking, S2S tornado prediction makes use of quantification of the environmental conditions that are important for tornado formation, such as vertical wind shear and the cape. Low frequency climate modes, including ENSO, MGO, and also global wind oscillation, can modulate tornado activity on the sub-seasonal timescale and often are used as predictors in statistical models. However, such low-frequency climate modes can only explain limited variability for tornado activity. Tornado outbreaks can still take place even when these low-frequency climate modes suggest an overall inactive time period. That is because of the modulation of the environmental conditions by synoptic scale processes. Here, we are going to test this hypothesis. Predictability exists for the statistics of the synoptic scale events, and effectively exploiting the this source of predictability can help us improve S2S prediction of tornado activity. The concept we use here is weather regimes. Weather regimes are recurrent atmospheric patterns. The underlying assumption for this concept is the large-scale atmospheric circulation can be represented by a finite number of states. This assumption is supported by theoretical work on the existence of multi-equilibria of the climate system. Since a weather regime can last for like a couple weeks, its persistence can serve as a source of predictability on the S2S timescale. Here, we are going to address two specific questions. First, how do weather regimes modulate tornado activity over the United States? Second, can we exploit the predictable information of weather regimes for S2S prediction? I will use observational analysis to address the first question and use the hybrid model to answer the second question. This slide shows the list of data sets used in the study. We used tornado reports from the Storm Prediction Center website. We focused on EF1 and stronger storms from 1990 to 2019. The ERA interim reanalysis was used to examine the environmental conditions. And we used reforecasts from ECMWF S2S model to develop a hybrid prediction model. Here, for brevity, I will just focus on May, the peak season for tornado activity. But I should mention the findings are also valid for March and April. So first, how do weather regimes modulate tornado activity? Using the key-mean cluster analysis, we identified 5 weather regimes over the United States. The number of the regimes or clusters is objectively determined using the elbow method. Here we can see the 5 regimes with decreasing frequency occurrence. The weather regime 1 is characterized by an elongated cyclonic circulation in the north and anticyclonic circulation in the southeast. And weather regime 4 is characterized by east-west dipole pattern. Okay. Now let's look at the link between weather regimes and the tornado occurrence. I showed the 5 weather regimes on the lower left for your information. The figure on the right shows is a kind of like a block plot showing the tornado occurrence. The x-axis shows the years from 1990 to 2019, and the y-axis shows the calendar days from May 1st to May 31st. The colors of a block represents the number of tornadoes per day, like the dark red color represents tornado occurrence with like at least 30 reports per day. And here we can see several outbreaks. You can also see, I should also mention the integers, the numbers here indicate weather regimes from regime 1 to regime 5. I can highlight a few examples. The tornado outbreak in May 2015, this one here, you can see it is associated with weather regime 4. And the outbreak in May 2019 is associated with persistent weather regime 1, which lasted for more than 10 days. Now let's look at some statistics. The bars here represent the percentage of weather regime days containing at least one tornado report. We have the 5 regimes represented by the 5 bars. Let's focus on the blue bar, which represent days with at least one tornado report. Here, the horizontal line represents a long-term mean, which is 55%. That means 55% of the days in the month of May are associated with at least one tornado report. The bars below the horizontal line represent below average tornado occurrence, and the bars above represent above average occurrence. In particular, we can see weather regime 1 is about 30% above the long-term mean. If you add the long-term mean number here, it indicates more than 75% of weather regime 1 days contain at least one tornado report. And weather regime 4 also contributes to higher above average tornado frequency. Now let's look at the environmental conditions. This is the basic plot. Here I show weather regime 1 and weather regime 4 as examples. The gray contours represent 500 millibar geopotential height. You can see the east-west dipole pattern for weather regime 4. The thick black contours represent Cape anomalies. Solid contours represent positive anomalies, and the dashed contours represent negative anomalies. Vectors represent 10 meter to 900 millibar wind shear. Purple colors represent where the wind shear magnitude is enhanced, and the blue color represent where the shear magnitude is reduced. You can see the shading I should mention. Shading represents tornado frequency anomalies. We can see both regimes contributed to enhanced Cape and vertical shear in the central part of the United States. And where the positive anomalies of Cape and vertical wind shear are co-located, we see enhanced tornado activity. Now let's take a quick look at persistent weather regimes. Here we define persistent weather regime as a regime that lasts for at least 3 days. We break down the total tornado days into 2 categories: those related to persistent weather regimes in the red bar, and those related to weather regimes lasting less than 3 days in the blue bar. About 75% of the tornado days are related to a persistent weather regime. Now, if we break this red bar down to different weather regimes, to the 5 weather regimes, you can see weather regime 1 and weather regime 4 associated with higher frequency occurrence than the other 3 regimes. In particular, 26 of tornado days 26% of the tornado days associated with a persistent weather regime 1 event, as indicated by this one here. Now let's look at the hybrid prediction. The hybrid prediction is based on the weather regime frequency predicted or produced by the ECM WF model. We found that the ECM WF model reproduces the spatial patterns of the weather regimes reasonably well. Then we examined the ensemble mean weather regime frequency, I should say weekly weather regime frequency. We used anomaly correlation between the predicted and observed weather regime frequency to assess the prediction scale. In the figure on the right, the x-axis shows lead time. We have day 1 to 7 to up to days 21 to 27. The different colors represent different regimes, and the black one represents the average across the 5 regimes. If we choose a subjective threshold 0.6, we can see the mean scale, the mean ACC is above 0.6 up to day 7 to days 13. That is week 2. Okay, to construct the hybrid prediction, we first calculated tornado frequency anomalies as a function of weather regime persistence, as indicated by the figure on the left. Here are again different colors represent the different regimes. The x-axis show the number of weather regime days per week. So if we use weather regime 1, this blue line as the example, you can see when its occurrence is less than 3 days per week, it is associated with weak tornado frequency anomalies and even negative tornado frequency anomalies. But with increasing occurrence, like when you have 5 or 6 days occurrence of weather regime 1 within a week, you can see it is associated with positive tornado frequency anomalies more than 1 day per week. Then we calculated the weekly frequency of model predicted weather regimes. Then based on the predicted weather regimes, we get we can predict the tornado activity. For example, it's if in 1 week we have weather regime 2 occurring for 5 days and weather regime 4 for 2 days. We simply add the anomalies here. This is minus 0.3. This is minus 1.8. When you add them together, you have about 2 days anomaly below the long-term mean. We use the leave 1 year out method to assess the prediction skill. We calculated the Hedicky skill score for 2-tier prediction, above and below average. The figure on the right shows the Hedicky skill score for United States, the whole continent, for as shown in the black curve. And the red one represents the southern plain, and the blue one represents Midwest. The x-axis again represents forecast lead time from day 1 to 7 to day 21 to 27. We can see we have positive skill score up to day 18 to 24. That is week 3. So okay, here is a quick conclusion. Large-scale weather regimes strongly modulate tornado activity, and persistent weather regimes associated with large percentages of tornado outbreak days. Hybrid prediction based on numerical model predicted weather regime frequency can produce skillful prediction out to week 3. This here we emphasize persistent weather regimes. When you combine this information with the forecast opportunity, we believe it can produce useful tornado prediction on the sub-seasonal time scale. Okay, that's it. Thank you.
Thank you, Dr. Wang. Karen, are there any questions in the document?
All right. I do not see any at this moment, no.
Okay.
I will stop sharing, I guess.
Yeah. Okay. I'm going to make our second speaker a presenter, and I think we'll stop recording now.